Good morning. Can you hear me over there in the back? Great. Okay, so before I get started, I want to acknowledge the funding sources, computational resources, and the people who did the work. So the primary funding for my corrosion work come from two DOE-funded centers. One is the Center for Predictive Integrated Structural Material Science, PRISMS. I heard some of you probably were here to learn about PRISMS PF earlier in this long program. And another center is molten salt in the extreme environment, where we are studying corrosion of metals in molten salt. We use computational resources from NSF as well as DOE, and also we use local computing resources at the University of Michigan. The work I'm going to describe today, the initial model development was done by Alex Chadwick and Steve DeWitt, also assisted in developing the computational software. More recently, Beck Andrews and Vicious Goel worked on the PRISMS work and on the corrosion side, and Ellery Hendricks and Beck Andrews also worked on the MC project, the molten salt project. Key collaborators are David Montiel from PRISM Center, who helps us with the software development, and Karen Chen Weigand and her group, who provides us with the microstructure information, micro measurements for the molten salt project. So just to recap, in tutorial 1, I actually talked about energy storage materials. So we looked at how you can model at the microstructure scale the electrochemical dynamics that is responsible for charging and discharging of battery electrodes. And then I continued on that in the tutorial 2, discussing how microstructure stochasticity, different, for example, in this particular case, particle size of active material amplifies the stochasticity that occurs in electrochemical dynamics. In the third session, it was a hands-on session that you were able to get your hands on the software that we use. And one of the example was actually corrosion example. And then today I'm going to talk about corrosion. So, and then you're going to see some of the similarities and maybe some differences as well in what I talk about with respect to the cases in electrochemical dynamics. So one important aspect of corrosion when you actually have multiple materials is this galvanic effect. So galvanic corrosion, when you have more noble metal and less noble metal, I mean, you could connect two metals, right? And then one is going to be more noble and the other one is going to be less noble. And then that leads to this current flow, like a cycle of a reaction that leads to enhanced corrosion. So the major issues have happened in for example, Statue of Liberty, where you have a copper and iron-based alloys, steel, connected with each other, and there was a coating, but then that failed and it started to degrade. But often, like you may, see something like this. I mean, in fact, in my house, it's an old house. There was a copper pipe and steel pipe, galvanized pipe was connected. And then indeed we saw something like this. Oops, sorry. And if you see something like this, right, like basically it was because you used, or somebody used the wrong material to combine. And so you have to pay attention to galvanic series. That basically it tells you how noble or more active a specific metal is. So in the case of Statue of Liberty, you have copper and iron, so you have this change in the potential, intrinsic potential of the metal, and that led to the corrosion. Now, the focus of Prism Center is advancing magnesium alloy as lightweight structural material. And so we look at the mechanical properties, but also it needs to withstand the environmental effect. And if you look at magnesium, it's extremely negative in potential, which makes it very susceptible to corrosion. So, and you may say, well, let's make sure that it's not in contact with other metals, right? However, when you alloy the material with other elements, which is necessary because pure magnesium is not going to be ductile enough to use it for the structural applications, you get this kind of microstructure. You solidify, and then you get this kind of blobs, as well as these fine lamellas. And so you can't really get away from having multiple metals present. And these things actually start the galvanic effect. So those lamellas are interesting. Also, we actually study with a phase field model. The phase diagram, some of you are not familiar with it. It tells you what phases are thermodynamically going to be expected to appear. So if you quench the liquid molten metal here, this is a aluminum copper example. Then at this composition, then you expect two solid phases to appear at the same time. In this case, aluminum and aluminum 2 copper, and you see something like this. It's a lamellar formation. And then that's because the diffusion in the liquid just in front of the solidification front controls this, how big the lamella can be. So, and it depends on the solidification speed. If you solidify very fast, you're going to get finer lamella. If you solidify very slowly, you're going to have a bigger spacing. So, and then if you go off eutectic, which is usually typical, like if you want aluminum alloy, you have larger volume fraction of aluminum-rich phase. So you go off eutectic, so you go here. And what happens is that you form a phase, the aluminum-rich phase here first, and the liquid follows this line. And then eventually, as the volume, you have a lot of, the aluminum-rich phase, there's going to be the copper-rich phase that segregates into, the liquid phase that segregates, and then it hits this eutectic point, and you have this structure that you saw earlier, where you form primary, and then you form the eutectic. Subsequent heat treatment can alter the microstructure like this, like if you just heat it up and then try to resolve the minority phase or at least coating them. So so we try to study these microstructural dependent corrosion dynamics using continuum-based description of what happens in the mechanisms that happens during the corrosion process, and it is based on the conservation law. So ionic transport in the electrolyte, which is a liquid, usually aqueous because it's like you may have seawater or whatever, and and then you have the electrostatic potential in the electrolyte. Compared to the battery problem, where you can have integration of lithium from the electrolyte to the solid. In this case, nothing that's integrating. So either whatever the deposition or the dissolution will move the interface, and that's handled using the phase field model that has this term that moves the interface based on the reaction rate, and the reaction rate is takes into account the sometimes local composition. In this case, we are just using the corrosion current and also the corrosion potential and the local electrostatic potential jump. Okay, and I think that I covered everything on the equation. And this was the equation that I showed you in the first tutorial. It's just really similar in terms of like how the reaction rate is described at the interface. The current continuity just gives you the electrostatic potential, and the mass conservation gives the evolution of the concentration. But how it's handled, how the reaction rate affects the interface is different. We now move the interface rather than letting the flux go into the solid phase. So here is a kind of example, simple example of pitting in single crystal. And we can observe how metal ion concentration changes as the corrosion occurs, as well as how the interface moves. So on the left-hand side, what you are seeing is the interfacial motion. So this is the corrosion front moving down, and this is accompanying metal ion concentration. So and then with this type of model, you can put a whole bunch of microstructural effects. For example, if you have a polycrystalline structure, then you can just put that into the system and describe some model of what the grain boundary wants to do. Grain boundary is usually more susceptible to corrosion, which can be modeled in terms of I naught change, the corrosion current coefficient change, or also you can put in a different corrosion potential. So you can actually simulate these, what would happen if you have polycrystalline structure, or what happens if you have more grain boundaries versus less grain boundaries. We can also put in the precipitates in addition. And then again, you can assign different electrochemical characteristics or properties for the precipitates. In this case, the precipitates are more susceptible to corrosion. And so you see these kind of rough interfaces, and clearly if you have a different amount of those second phase, you're going to see a different corrosion rate. So we have those things implemented into Prism's PF. It's an open source parallel phase field modeling framework with advanced capabilities. I'm not going to say too much about it because I talked about it during the tutorial. But it is, if you just want to take an app and then run it, it's very, very quick. And it can be also modified for your own needs. And we are here to collaborate and help. So if you are interested in trying it out for your research, please let us know. So Prism's PF have a whole bunch of applications, like coarsening, grain growth, etc. There are about 30. And two of the applications are on corrosion. And the software implementation is described mainly in this paper. There's also generic Prism's PS paper from 2020, but those are focused on the corrosion itself. And this paper in particular describes more of a microstructural effect. So simulation setup usually looks like this. You have electrolyte, magnesium-rich phase, and aluminum-rich phase. I forgot to mention that the microstructure I showed you, that is a magnesium alloy called the AG, what was the number? I forgot. AG something. And then it has aluminum, 9% I think, and 1% zinc. So there's a more aluminum-rich phase better, and magnesium-rich. They both have magnesium, but they're two phases with different compositions. So to examine different microstructures, because we took advantage of laminar structure because it's kind of like pseudo 2D, right? So we just took a cross section and then did a 2D simulation to examine how different microstructure leads to different corrosion properties. So wide lamella, medium lamella, narrow lamella, and the lamella region kind of close together with the next to larger alpha region. And so these are initial structure, and these are the simulation result at 600 seconds. And you can actually easily see that the corrosion rate increases with narrower distribution. By the way, I forgot to mention, the volume fraction here is the same for all of them. So it's 21% beta phase. So, you often hear, you don't want to have larger volume of cathode material, but here the volume is the same, but the corrosion behavior is different. So, and then you can quantify what the corrosion is, how much corrosion is occurring by looking at the corrosion current, because that's basically the flux coming out. So, and the case 4 is this one with 3 narrow lamellas are kind of like compressed in one side, and then there's larger lamella. The case 1 is the widest one. Case 3 is narrow but uniformly distributed. In all cases, the rate increases with time, right? You can see how the corrosion is accelerating. And then you can also see that the finer the lamella is, the larger the corrosion rate is. So the question is why? And that's because as the corrosion occurs, the cathode area gets exposed more and more and more. So as I go back here, I probably should have had a video here. But as this one corrodes a little bit, you have this much surface area gets exposed, right? So there's more cathodic area. And then as it this interface goes down, you have more of these, right? And then the finer they are, the more of those lamellas. So you have more of them, at the same amount of corrosion. So that's what we are seeing here. And so we plotted here is a surface area of the beta phase that's exposed to the electrolyte. And we see the same behavior as what you see in corrosion current. Here, I did not overplot on top of each other because it is not like same quantity. But I can tell you that case 1 and case 2 actually overlaps very, very well. The case 3 and case 4 starts to have, at some point, it starts to have this nonlinear effect, especially because of the limiting current. So because of diffusion, you start having difficulty actually, corroding at the same rate. And then that slows it down, and then you see that this increase is less than what you see over here. So you can actually learn quite a bit by just looking at these time evolution of quantities and how they compare with geometric quantities. So and then with microgalvanic corrosion with microstructure, there's this positive feedback to encourage the corrosion rate to go up, increase with time, because as the corrosion happens, there's more beta phase that appears. Surface that are in contact with the electrolyte, and the cathodic effect becomes larger and larger and larger. So you get this even faster corrosion as the time goes. And as I pointed out, it's not the volume of the cathodic component, but the area that matters. We also studied other quantities, like what material properties are important in corrosion. I'm just going to show you one example here, so that I can also talk about molten salt. So cap here is the ionic conductivity of electrolyte. This sub E is electrolyte, and so what you can see here, and then the simulation was similar like this, right? Except we kept the same microstructure, but we changed this parameter, model parameter. So initially, the lower conductivity case has lower corrosion current. So it seems like, at least initially it looks great, right? It's a lower corrosion current. That's better. However, as the time goes, there's this crossover, and then actually if the lower conductivity is lower, the current becomes larger later on. And it can be understood it's because of this non-uniform corrosion. So you have this beta phase region. This is the front. It starts out with flat, right? All of them start out flat. When you have the higher ionic conductivity, this surface, the alpha phase, surface is just receding uniformly, okay, just corrodes uniformly. However, and then because of that, you have a higher rate to start with. However, for the and then with time it also increases because there's going to be more beta phase surface that's exposed to the electrolyte. However, if they have lower conductivity, then what we saw is this kind of non-uniform corrosion front. So there's going to be higher corrosion rate near the beta and lower further away, which means that you are taking more out, more alpha phase out, corroding alpha phase near beta phase. So there's actually more surface area of beta phase that's exposed with time. So then eventually this effect, microgalvanic effect, and a larger surface of beta phase is going to take it over. Then that's where this crossover happens, and then this one keeps going up because you have more beta phase exposed. So this uniform corrosion front seems to be an important quantity. So we looked at, there's some literature, and there's this article from the 50s by Wagner, and he suggests this quantity. It's a length scale that is multiplicative factor of the conductivity and this D. It's probably easier to understand this by looking at D, I reaction, D over potential, and inverse of that. So that ratio is the length scale. And this governs how uniform the corrosion rate is going to be. So you can think of Wagner length as a characteristic length for transition over, there's some length scale that over which ionic transport is efficient enough to keep the current density to be uniform to the order of magnitude. So when the characteristic length scale of microstructure is much smaller than this Wagner length, then you get uniform corrosion. And if you have much less than non-uniform corrosion. So this is there's actually material property also in I reaction. So this includes the material properties, but also the microstructure, because this characteristic length scale for microstructure is microstructure dependent. So we have this kind of non-dimensional number analysis, which in case in this one is this divided by this, that's a non-dimensional number, is useful because you can always make some statement without doing detailed calculation. But we do have the detailed calculation. You can calculate the Wagner length actually minimum because it actually changes with at a different location. So and then if you have this larger conductivity, as you saw before, you get this. We saw that this you have a uniform corrosion front, and indeed this is much larger than the length scale of this microstructure, which is right here. So anywhere, well over this line, far from, far above this line, you expect the uniform corrosion. And then when it goes below this, there's going to be this non-uniform corrosion that occurs. We look at this and also in 3D, and we see this basically, similar effect. Similar behavior in corrosion. So this kind of simplified picture can also be applied. Applicable to real or three-dimensional corrosion. I wouldn't say real because you never know. The parameters are always difficult. Oops. Okay. Yeah, that's fine. Yeah. Okay. So I'm going to switch the gear and talk about molten salt reactors. Corrosion is, relatively well understood in aqueous solutions because, there's a large body of work in corrosion in aqueous solutions. But, of course, water makes it difficult. But in terms of data, right, like the model parameters, it's often, easy to find. Whether that's right or not, that's always a question. And but with molten salt, it's just not there. so it's been a challenge. Why do we want to have molten salt? And there are many applications of molten salt, including even batteries. But for nuclear reactors, it's used as coolant here, right? And unlike water, if there's an accident, it's not going to blow up, right? You're not going to get evaporation of molten salt. So there's this added safety. It's also it blocks radiation quite well. So this potentially allows small-scale nuclear reactors that are safer, can be around, people can live around easily, etc. But you have to somehow contain these molten salt in some structured material, and it's a totally different game. You got high temperature, you got ions everywhere, right? It's ionic compound that's molten, so it's charges everywhere, and not just polarized molecule, right? And then dissolving some salt. This is actually just the salt. And so it's difficult. So physics and chemistry of molten salt is not quite well developed or well understood. And then there's impurities as well as solute that comes out in application. Actinizers sometimes in there. Fission products are there. Corrosion products are there, and then all that changes the dynamics of corrosion. And so the interaction with molten salt with other reactor materials, such as just containment, is a big challenge. And this kind of illustrates how crazy it is, right? Like this is a thin wire. And it's a tomography cross-section from a tomography. And depending on the condition, low temperature, high temperature, it's either way, you have this very fast corrosion and de-alloying, formation of polar structure. So this is what's going to happen to the surface of metal, right? And so we have to understand what that means to the mechanical integrity of the material. So my collaborator at Stony Brook University and Brookhaven National Lab, Karen Jane Weiger that I mentioned earlier, and her group have been studying nickel-chromium wire put in the molten salt. The molten salt mixture usually are kind of like near eutectic composition that allows it to melt at lower temperature. So usually there are, this is chloride salt, but then there are two metallic cation species in addition. So you have at least three components in the salt. And they see processes such as surface corrosion, intergranular corrosion, percolation dealloying, and surface diffusion, or some kind of diffusion mechanism that causes this microstructure. So if you look at the porosity, there are actually multiple distinct stages. So there's usually this rapid corrosion that happens, and then at some point the porosity kind of gets saturated, and that's because nickel is relatively stable, and then you have this coarsening that takes place. So this really is in a intermediate stage, it's actually both coarsening and the corrosion happening at the same time. And as a first step, we tried to separate the different stages. First, we weren't sure what mechanism is responsible for coarsening. So we started to look at the coarsening first, and then we are now doing more of a corrosion work in this. So I'm just going to briefly mention the 3D coarsening simulations that we've done, and then kind of illustrates how we are going to keep, approach corrosion work as well. So we start with the initial condition from X-ray tomography. We take the time step from which we are pretty certain that the corrosion is done. And then we process the data, and then we coarsen. So we have multiple hypotheses, and we have to figure out which one is more right. So bulk diffusion through solid, bulk diffusion through liquid, and surface diffusion. Those are 3 separate simulations that we conducted, and that we can do get the microstructures at different times. So actually, a whole bunch of simulation just continuous in time. So we have 3 simulations, whole bunch of data as a function of time. And then we did quantify the morphologies so that we can compare them. Even though this is 3D experiment and 3D simulation, actually 4D experiment and I guess 4D data from the simulation, we can't actually do point-by-point comparison. And the reason is that in the tomography, this is wire, and it's like, it's like jiggling, sometimes even drifting up and down. And then that made it completely impossible to do point-by-point comparison. So we had to do something, and what we looked at multiple kind of quantities. Like things like a porosity was just too close to even distinguish different mechanisms. And so we decided to look at the radial density function. So just looking at how much solid there is from the center of the wire. And then this schematic is 2D, but it's actually all in 3D. And then we did a comparison of difference between what's predicted. So the red curve is the initial condition, but the blue curve is a prediction for the solid, and the experimental data is dotted. And then we took those differences, we plotted them as a function of all the simulation time and experimental time, and we find this matching, how basically the scaling time between the two. Just looking at the error, we were not able to distinguish the bulk diffusion and surface diffusion. So we had to look at the actual quantities, or basically back calculate the diffusivity out of that, and then compare with the literature values. With that, we were able to say that surface diffusion is most likely mechanism, even though bulk diffusion could still be in the running if there are a lot of vacancies injected into the solid due to the de-alloying process. So, so then we continue to look at the corrosion. So we looked at the surface corrosion, intergranular corrosion. De-alloying is something we are still working on. Other process, grain boundary diffusion, and actually, yeah, we're just having to check. And then stress effect grain growth. So, so maybe I should just, I think I talked about the model, already, but basically we are following the solid interface. This is 2D simulation, so it looks like separated, but we are not actually modeling, it may be attached out of the plane. We started out with pure metal, and so those are the equations. Left side here is the surface corrosion only, and it's running, it's slow, but it's a flat, gradual corrosion. So this is just one single metal, and the grain growth is observed. Right side is with grain boundary diffusion, and it's going to be more rapid because we actually enhance the rate there. One of the things that I observed in the experiment is a nanoparticle formation, and this kind of like grain boundary corrosion, grain boundary attack can lead to grains falling out, which may explain those nanoparticle formation. So, so we demonstrated that the intergranular corrosion can be modeled with grain growth. So it's a kind of multi-physics model that we developed. And then the detachment is exaggerated in 2D, but it could also be, it could also explain nanoparticle formation in the experiment. We also looked at the microstructural effects on the corrosion behavior for the pure case. And this is the result at the 150 seconds. And this is the wider grain sizes. And then you can see that actually this like a wider grain size case has a more penetration, which I thought was a little bit unintuitive. But then we realized that the small grains actually like dissolves and then gives this kind of fast path of electrolyte fast path of ionic transport through penetrated wider electrolyte path. So so that makes sense. And we recently added the alloy corrosion, and this is the result of alloy corrosion. What we saw is like this, kind of boring, right? And just you see the gradient in the chromium concentration, which is actually not consistent with the experiments. So we had to actually look at other mechanisms. So this is including grain boundary diffusivity, enhanced grain boundary diffusivity. And then now we could get this, what they were observing in experiments. It's kind of hard to see, but there is basically the region where chromium is depleted, just like you see over here. So that might be the how the what might be important. So this is a bit preliminary, but this is what we recently found. So we are working towards the morphological phase diagram of metals in molten salt. So it's going to depend on what material they are. It's going to depend on whether salt has some impurities, and it definitely depends on temperature. So, so that's where we are. This is where we want to get to. So as a takeaway, we developed an open source software applications in Prism's PF for material science community to simulate corrosion. So if anybody is interested, please contact me. And I presented two example applications, corrosion in magnesium alloy, and the other one is molten salt. And then it's informed by experiments that are tightly coupled. In terms of microstructural effects, because I feel like that's what I'm here for, to tell you, surface area of cathodic material has a strong effect on how corrosion is accelerated. Grain size distribution has an important consequence on the grain boundary corrosion. And grain boundary diffusion may also be important in molten salt corrosion. And this is what I think is interesting, at least in the context of this workshop. Electrochemical processes can amplify the stochasticity that exists in the microstructure. And I really want to get at this question. How can we take this into account on a coarse-grained model? Because you don't actually want to do those detailed simulations all the time, right? You want to come up with something simple, like porous electrode theory for the battery, but maybe something like porous electrode theory of the corrosion. And that's what I really want to think about while I'm here. Thank you very much.